Welcome to the American Mathematical Society Invited Address in the Joint Mathematical Meeting 2021. I am Cristina Pereira from the University of New Mexico. It is an honor to introduce today's speaker and dear friend, Andrea Nahmod. I have known Andrea Nahmod since we were graduate students at Yale. Both of us, both of us came to the US encouraged by the late Cora Sadowski. Andrea Nahmod received her licenciatura from the University of Buenos Aires and her PhD from Yale University under the supervision of Ronald Koifman. After postdoctoral positions at Macquarie University, University of Texas at Austin, and the Institute for Advanced Studies at Princeton, she joined the faculty at the University of Massachusetts Amherst, where she is now a professor. Professor Nahmod's research interests lie at the interface of nonlinear Fourier analysis and harmonic analysis and the theory of partial differential equations. She has made fundamental contributions to the understanding of bilinear pseudo-differential operators and dynamics of nonlinear waves. In the last 15 years, she has done leading research at the forefront of nonlinear partial differential equations aimed at gaining understanding the effect of randomness in the evolution of nonlinear waves in various regimes. We will learn more about this in her talk. In 2014, Professor Nahmod was named a Fellow of the American Mathematical Society. She is a recipient of a Radcliffe Sargent-Fold Fellowship and a highly competitive Simons Foundation Fellowship. She has been twice a member of the Institute for Advanced Study at Princeton. She has had NSF support since 1999 and is currently a PI of a multi-institution, multi-million large Simons collaboration grant across continents on wave turbulence. Her professional service is quite extensive, including service to the National Science Foundation and other international research foundations, service to the American Mathematical Society, organizer of semester-long programs at math institutes, and a long, etc. Professor Nahmod is not only a first-rate mathematician and good citizen of our community, she is also a dedicated teacher and mentor. Numerous postdocs, graduate and undergraduate students have benefited from her deep knowledge and steady encouragement. As a product of the public school system in Argentina, and a life dedicated to a public institution, Professor Nahmod knows that talent can be found anywhere, and the same way she was helped when she was young, this needs to be paid forward. A set of values shared by all the organizations behind this wonderful meeting, the American Mathematical Society, MAA, AWM, NAM, SIAM, and all. It is a pleasure to have Andrea Nahmod speaking today.
First of all, let me thank Cristina for that very kind introduction. And I would like to thank deeply the Joint Mathematical Meeting and volunteers who have put an enormous amount of effort and time in and through quite a few years to prepare for this meeting, and done a fantastic job. And I would also like to thank the American Mathematical Society for this opportunity to speak here today. I hope that you hear me all. If you don't, Cristina will let me know. So let me actually start a little bit by trying to tell you a little bit about what's the motivation behind of this. So what is it that we would like to understand? We would like to understand and describe how genetic data in the sense of probability, that is random initial data, gets transported under the flow of a dispersive process. And I will tell you what the meaning of this word means. But the why we want to do this is because randomness is everywhere in our physical world and natural world. Despite how much we long for certainty, things are pretty random. And but from the scientific point of view, sort of like this this problem arises naturally in various contexts when studying wave phenomena, like the study of Gibbs measures in sort of, for example, statistical mechanics, wave turbulence, and the Cauchy theory for PDE in various regimes. So the goal of this talk is to tell you a little bit about how this area has developed and describe the theory of random tensors, which is joint work with my two dear collaborators, Yu Deng and Hei-Tian Yu, who was also my former PhD student. So the areas involved that you're going to see are, of course, partial differential equations, nonlinear Fourier analysis, harmonic analysis, probability, analytic number theory, combinatorics, and others. And it's thanks to the sort of like the combination of ideas and insights coming from all these fields that progress has been possible. So let me say, okay, what is dispersion? So we are all familiar with dispersion since we observe it all the time when you see a rainbow. So the dispersion causes the spatial separations of white light into the different colors. Or when you throw a pebble in a lake or in a pond, then you see these ripples, which are these expanding rings that are called mathematically wave packets. And what you know is that individual waves travel at different speeds, the longest ones going fastest than the shortest one, which goes lowest. So what dispersion means is that when no boundary is present, like suppose that you're in a gigantic lake and you don't see sort of the coast or the edges, then waves of different wavelengths travel at different phase speeds. And as I said a minute ago, long wavelength components propagate faster than shorter ones. So this is the reason why dispersive waves spread out in space. So this like this idea of the lake, they spread out in space as they evolve, but they conserve some form of energy. And dispersive wave phenomena is something that if you have taken a class in PDE, the first thing that they show you is transport phenomena. And transport phenomena doesn't have this property because they are all frequencies travel or move at the same velocity. Or dissipative phenomena or diffusion processes like the heat equation, in which frequencies gradually taper to zero, that is, they do not propagate. So dispersive processes are very different than these two other phenomena, okay? And the equation par excellence, if you wish, the most ubiquitous one to study or that represents dispersive phenomena is the nonlinear Schrodinger equation. So mathematically, the nonlinear Schrodinger equation as a model, you use it and you see it also most of the time because, for example, we all enjoy digital communications. So you see it in fiber optics or nonlinear optics. You see it in the ocean in sort of like these gravity waves when, for example, at the interface between air and water. But you see it in the well-known Bose-Einstein condensate, where the profile that you see here is the profile of a solution of a nonlinear Schrodinger equation. So let's get to math. So here what we have is the equation itself. I mean, what it is, I, the derivative of u, you have a function u that I'm going to focus myself on the underlying space is going to be a torus, a periodic box, if you wish. And so you have I, the derivative of u with respect to t plus Laplacian of u equals to some nonlinear term, which is a polynomial or power multilinear nonlinearity of order p. So the reason why it's written like this is because u is a complex value function. So you need p minus 1 to be even. So the p is always odd. And so this here is simply, if you are cubic, all you're doing is you're taking u bar u, that's your u square u, that's cubic. And if you're quintic, then you have u bar u bar u, that's u to the fourth u. And for example, when I mentioned the Bose-Einstein condensate, for example, it's like the cubic is the one that arises naturally when you have this binary interaction of bosons. And this is actually comes from the celebrated work of Erdős, Schlein, and H.T. Yao, and in 3 dimensions. And for example, the quintic arises also naturally when you are in a sort of a rectangular box in 2 dimensions, when instead of binary interactions of bosons, you look at the ternary interactions of bosons. And this actually was something that was shown in the work of Thomas Chen and Natasha Pavlovich. So this equation enjoys lots of symmetries and enjoys certain conserved quantities, but let me just mention one, which is the fact that this equation is what is called a Hamiltonian. I mean, it has a conservation law, which is simply 1/2 of the gradient of u squared plus 1/p+1 u to the p+1. So lambda here, I didn't say it, is only either plus or minus 1. And I'm only going to take it to be 1, so you can completely ignore it. But it accounts for the name of focusing or defocusing equations, because if lambda is 1, this is a positive, is a coercive quantity, it's positive. But if lambda is minus 1, then this is a minus, and then you have trouble. So focusing problems are hard. But you can forget about that. So what does it mean that this is a conserved quantity? It means that you see this quantity depends on t, but as time goes by, this quantity never changes. So that means that it's the same whether I put t equals to 1 or I put t equals to 0. This is a constant of time. Okay, and I'm going to use this h, this Hamiltonian. So I need you to remember the notation. So there is, of course, the nonlinear Schrodinger equation can be considered on other underlying spaces where X is not on in a periodic box, but is, for example, in the whole space or in some compact manifolds. But actually, dispersion, the notion of dispersion when you're in a periodic box is weaker than on infinite space. And the reason is, if you remember that lake, is because waves expand, but if they hit the boundary, like at the shore, then the waves will come back to themselves and self-interact. So there is a lot of different and interesting phenomena that happens when you are in the periodic case. Okay, so so of course you can never understand a nonlinear equation. This is what you tell your students. You can never understand a nonlinear equation if you first don't understand the linear equation. So the linear equation is when you ignore the nonlinearity and you just look at the equation where is I ut plus compression of u equals to 0 and you look at the Cauchy problem with initial data u0. So you want to know, if I give you a function u0 in some function space, can I find the solution u? And of course, when you're linear, you can do this explicitly, and the solution can be written explicitly as a semigroup that we write as e to the it Laplacian times u, which actually is computed, for example, if you can use the Fourier transform as simply the anti-Fourier transform of e to the minus it mod k square times the Fourier transform of the initial data at k. So if you're in a periodic case, on the Fourier side, you are on ZD instead of CD. And so what is dispersion, or the dispersion relation, tells you that the wave frequency, which is omega, I mean, it gives you a relationship between the wave frequency omega and the wave number k. And in here, it tells you that this is equal to minus k squared, right? That comes from the Laplacian here. And so in other words, is that if you take omega and you divide it by k, that's the phase velocity, then you get something that actually goes to infinity as k goes to infinity. So the semigroup, which is the operator that gives you the solution here, is a very nice operator that preserves the L2 norm and also preserves the Sobolev norms. In other words, it preserves the norms of functions which are in L2, and they have S derivatives also in L2. And so you have a very nice theory in the Sobolev, in the L2 base spaces, okay? But this is not bounded on any other LP space. So if I change L2 by L4 or L3, or the Sobolev space based in L2 by another one based in LP, then this doesn't behave nicely. So you don't have a nice theory. In the same way that you don't have a nice theory on Helder spaces or in infinity, which is a big difference, for example, with heat equation, with diffusion processes. And so this is the reason why what we do is we look at the H theory for the nonlinear equation what that means is that we study the problem, the nonlinear problem, with data in HS. And so the first question that I want to answer, or I want to understand, is for what regularity, how smooth the data should be, what is the S that I can take so that I can produce a solution to this problem. So where can I take U so that this problem has a solution? In other words, I can find a solution that is unique and that is bounded. If I start in HS, it's also bounded in HS for the time of existence, for the time in which it exists. So in order to understand that question, I'm going to do a calculation, which is just like a little bit back of the envelope calculation, which is the scaling argument that tells you a necessary condition for S. So we take a very nice and simple initial data. That means I'm going to take a function which is a single frequency. So the frequency of F is just always of order capital N. And the Fourier modes are constant, 1 over n to the alpha. And alpha is going to be, if you give me an F, alpha is going to be S plus the dimension over 2. And remember this because it's going to come over and over and over again. So this is a very special initial data, okay? So I want to do a calculation. I want to make my life easy. We take a very easy initial data. And you can actually check that this function has a norm in the HS that you give me that is of order 1. So what the Duhamel principle tells you is that you can write a solution of the nonlinear problem in an integral form as the linear evolution of your data F minus the Duhamel term, which is simply the inversion of the Schrodinger operator onto the nonlinearity, okay? So if you think about Picard iterations or iterations, if you have any hope of having a solution, then it should be that when you plug in here, instead of, when you plug in here the linear evolution, which is what we call the second iteration, then that stays bounded in HS. If I started bounded in HS, when I plug in here the linear evolution, I should get something that is still bounded in HS. So that's what I call U1. U1 is just the Duhamel piece. This curly I is simply the Duhamel term. And what you want is this to be bounded in HS. And so the way that you do it is you take the Fourier transform of this, and this is okay, some factor that we can ignore. Then you have n to the minus p alpha, which comes because I have p functions of frequency 1 over n to the alpha, and then you have the term that comes from the Duhamel operator here, okay, which is simply the sum you have when you take Fourier transform. This as the product, you get a convolution, so you have the sum over k1 minus k2 plus k3. The plus and minus is because you have a complex conjugate, right? So whenever there is a complex conjugate, you get a minus, if not, you get a plus. All frequencies are the same of all the functions because they're all n. And then you get the integral from 0 to t of e to the is omega. And comes from these terms, from the if you wish, the temporal Fourier transform. And so one can actually do that or see that this term is actually bounded by 1 over the size of omega. And here I put a Japanese bracket because I'm going to take this to be 0 in a moment, and I want this to be 1 plus omega, okay? So as I said, if you look at this, then the Fourier transform is simply n to the minus p alpha times the sum of 1 over omega. And we want to find a bound that is independent of what is the size of omega. So I'm going to just take omega to be 0. In other words, I'm going to take in this resonant relationship, I'm going to take k squared, which is the output of all the frequencies, to be k1 squared, minus k2 squared plus blah, blah, blah. So if you actually set up omega equals to 0, so then here what you're doing is you're just summing 1. So you're trying to understand what is the cardinality of this set. Okay, so if you do a dimension counting, this is like elementary number theory, you get that this is of the order of n to the minus p alpha, and the size of this is n to the p times the dimension minus the dimension minus 2. Okay, you have to trust me on that because I'm not going to do it. And so if you want to know, if you want to have this U1 to be bounded in the same subwhole space as you started, then what that means is that if you take n to the minus p alpha times n to the p d minus d over 2, and you add s plus d over 2, okay, which is what comes from taking this norm, then that should be a negative number so that you get something bounded. And if you do the calculation, this is alpha is s plus d over 2, then that means that alpha should be bigger than d minus 2 over p minus 1, which means that the s that you give me must be larger than the dimension over 2 minus 2 over p minus 1. So if you are cubic, you should be bigger than the dimension over 2 minus 1, for example. And this is actually a necessary condition in order to be bounded. So this number here is what is called, deterministically, what is called the scaling critical exponent for the nonlinear Schrodinger equation. And there is this sort of idea that if this critical index is positive, then, and your regularity is larger than that, this is what we call subcritical, then you always have solutions. Local well-posing is that you always have a solution, they have existence uniqueness of a strong solutions. That means the solutions which are in HS for the time of existence. And this actually is a theorem that follows from very famous estimates called the Strickers estimates and so on. But if I ask the question, okay, what happens if S is equal to the critical? This is actually what we call the critical case. Like, for example, what happens if you are in L2, okay? Then the cubic equation in 2 dimensions. Actually, this result is unknown. Nobody knows if there are any solutions at all, which is incredible, right? You take the cubic equation in 2 dimensions in the periodic case with data in L2, you don't know if you have any solutions, okay? And things get worse if you become rougher. So if you take regularities which are lower than this critical exponent, which is called supercritical data, then actually you might have some failure in the existence. You can have some failure, which is what we call impulsiveness. You know, the stability might fail, or it could be worse. So let me not dwell into this. So the question that we are interested in is in knowing, okay, then what happens generically? Okay, in other words, I don't want to take every single data in HS, but I want to know what happens if I take some generic data in the sense of probability. So in other words, what happens if I randomize the data and I study generically what happens with solutions? Can I actually improve and say and tell you something more about these cases which are bad, okay, deterministically bad? And so this approach is also physically meaningful and is linked to the statistical ensemble point of view, in which instead of studying an individual solution, another law like the Gaussian law. Okay, what we are going to do is we are going to go from a deterministic point of view to a non-deterministic point of view, and we are going to be doing so. Please come back. And the way that we are going to inject some randomness into our problem is through the random data. This is not the only way, of course, right? But it's one way, and this is the way that we are going to focus today. So what is behind the basic tool from probability that comes into play is the large deviation estimate. So what we are going to do is we are going to consider a family of Gaussian IID, so independent and identically distributed Gaussian random variables, which I'm going to call GK of omega. There is omegas in some probability space, which I haven't written. And so what you know is that there exists a constant delta and another constant lambda, such that if you give me a sequence in L2, the probability that this random variable, which is the sum over k of vk, gk being bigger than lambda, actually has and exponentially decaying tail is less than or equal than e to the minus delta times lambda square over the L2 norm square of the V. So what does that mean? What that means, I mean, if you use Chebyshev, is that for any A, if you take the absolute value of this random variable, essentially with high probability, it's as if you can put the absolute value square of here, you can put the absolute value square inside the sum, okay, with no penalty. Okay, so with high probability, the square of this is less than or equal than simply the square of the decays, which you know is finite because you're in L2. Okay, and there is similar results which are a little bit more sophisticated for what we call multilinear expressions of Gaussians, which are the ones that are behind our work, but I'm not going to state. So actually, this gives you something very nice and very sort of a old result, which says that, you know, this implies that if you take, for example, a random series where instead of taking little L2 coefficients, you alternate, you put plus minus 1 in front of them, you randomize the coefficients, then this function, instead of being just in L2, because the AKs are only in L2, they are actually in LP for any p bigger than 2. So in other words, randomizing the Fourier coefficient gives you a tremendous gain in integrability, but it does not give you a gain in smoothness. Okay, and these are all results actually. You know, they go back to the 30s. So the random data theory means that that's how we are going to randomize our data. We are going to take a function with Fourier coefficients, which are going to be simply 1 over k to the alpha, same alpha. And I'm going to randomize the 1 over k is the Fourier coefficients. I'm taking a specific sequence of Fourier coefficients, and you randomize them with some Gaussian random variable. Okay. And so the law distribution for this function is a Gaussian measure, okay, which is written here. But what is important is that actually the support of this Gaussian measure is in HS minus. So that means that if you give me an S and you take alpha to be S plus D over 2, then this function here, okay, belongs almost surely to the space HS minus epsilon. So in other words, it doesn't belong to HS. It's a little bit rougher than HS. Okay, it belongs to HS minus. Okay, so this point of view of taking this random data by changing to this point of view, actually we can pass this barrier in the deterministic case, which was given by the scaling barrier, and actually get almost sure get existence and uniqueness of strong solutions for values which are rougher, which are supercritical, which are below the critical index. So historically, people only knew weak solutions in this sense, but they didn't know anything about strong solutions or uniqueness. And it was not until the seminal work of Bourgain in '96 that he showed that if you actually do this randomization, then you can break this barrier. And for some regularity below the critical, you can actually get strong solutions. And so I like very much this analogy from my collaborator, Yu Deng, who always says, and I like it, says, well, you know, these almost sure strong solutions are not very mysterious. They are to classical solutions as measurable functions are to continuous functions, okay? So they should be friendly guys. So there have been lots of follow-up works after Bourgain's, but the fundamental questions that remain is what are the optimal values of S for which you can get these? Bourgain went a little bit below, but how far can you go? Which is the optimal value? And then more importantly, you want to actually understand how this Gaussian random initial data gets transported, gets sort of propagates under the nonlinear Schrodinger flow. That means if you take Gaussian initial data, then what is going to happen? How is this going to propagate? Can you tell me, can you give me a description of the solution beyond the linear evolution, right? I mean, the linear evolution of something that is random, it will be also Gaussian, but then what happens to first order? What happens with the next term? How does it look like? So such questions are very important in many topics, such as, for example, the invariance of Gibbs measures, which appears in statistical mechanics, constructive quantum field theory, stochastic TDE. And also in wave turbulence, which I don't have time to go into, but I put here some very important references for you to take a look. So let me talk a little bit about the invariance of Gibbs measures. And so when you are, what happens is if you take alpha equals to 1 here, instead of any alpha, you fix 1, then this data always represents a typical element in the support of a Gibbs measure that is associated to the Schrödinger equation. And Gibbs measures are actually something very nice objects that lie at the intersection between PVE and statistical physics. So there is a lot of mathematics and a lot of points of view that come into play that you can understand. Is a very rich thing to study and understand. And so, but what happened, if you remember before that I told you where this function lives, what happens is that if you're in dimensions 2 or dimension 3, this function is actually quite rough. It's a distribution. If you're in dimensions 2, it's something that belongs, it's a distribution that is not in L2, it's below L2. That's what I mean by 0 minus. 0 minus means that I'm below L2. And if you're in 3 dimensions, it's even worse. It's actually a distribution that is extremely rough. It's in minus a half minus, okay? So it's really, really rough. And so from the Hamiltonian structure of the Schrödinger equation, if you remember the Hamiltonian, you can actually formally think of the Gibbs measure as being the exponential of minus the Hamiltonian times the Lebesgue measure. And of course, the way that I have written this makes no sense because you cannot write the Lebesgue measure this way in infinite dimensions. But in many cases, actually, if you undo the Hamiltonian between the kinetic, if you put the kinetic energy together with the Lebesgue measure, that gives you this Gaussian measure with alpha equals to 1. And then the potential energy gives you a weight. And so many times you can make sense of this measure rigorously as a weighted Gaussian measure, okay? And you can think that it's invariant because Liouville will tell you that this part is invariant, and the fact that the Hamiltonian is conserved will tell you that this is invariant. Invariant means that if I give you a set in the support of the measure, and I somehow flow that set by the nonlinear Schrödinger equation, so if I actually let it flow, then at a later time, the measure of the initial set and the measure of the set at time t is the new measure is going to be the same. That's what invariance means, okay? And so all of this is very formal, but the construction and the dynamical properties of these measures has been a very important and major problem in statistical mechanics, constructive field theory, and in constructive quantum field theory is very intimately related to what is called the phi-4 model, okay? So there's 2 aspects to these measures. One is the construction. So the construction can be done in dimensions 1 and 2 for any power, odd power p. And in that case, you get a weighted Gaussian measure, which is absolutely continuous. You get a Gibbs measure, which is absolutely continuous with respect to the Gaussian. In dimension 3, however, the construction can be done only for p equals 3. It's not expected for any other p. And not to the measure, okay, which is a big problem. Yes?
We lost you a little bit, but you're back.
Okay. And in dimensions bigger or equal than 4, it cannot be done. So that's the construction. How about the invariance? So the invariance of the NLS, in order to talk about invariance, you need to know that you have global solutions. So what about the invariance of the measure? Together with the existence of global strong solutions for data which is in the support of a measure. That's the statistical ensemble. So the difficulty for the dynamics, as I said, is that the Gibbs measure is supported in very rough spaces. So the invariance of the measure was only justified in the mid-90s by Bourgain in dimensions 1 for any p bigger or equal than 3. And in dimensions 2, it was only justified for p equals to 3, and I'm going to tell you why. And although the measure can be constructed for other p's in dimensions 2, it was open since Bourgain's work until 2019, what happens with the invariance and the existence of global strong solutions if you have a p equals to 5 or any other larger p. And this is actually something that we solved last year with Yudeng and Haitian. And how about dimension 3 and p equals to 3, for which you haven't measured? Then that's an open problem and it's very hard. And I'm also going to tell you why it's very hard. So what are the fundamental questions? The fundamental questions are, what is the optimal value? I'm repeating the questions that I posed before. What is the optimal value F for almost sure local well poses to hold? How does the initial random data get transported? And then let's go if it's Gaussian initially, how this Gaussianity propagates. Where is the description of the solution beyond the linear evolution? And can we prove the invariance of the measure in dimensions 2 for any p odd? And the question is also, why is it? So if you look at the dimension 3 and the cubic problem in dimension 3, the critical scaling is 1/2. And if you look at the equation in dimensions 2 and p equals to 5, the critical index is also 1/2. We can solve this problem, but we cannot solve this problem. Then the question is why? Why is this problem so much harder than this problem? So the answer to that comes from, we answer all these questions actually, and with Yudeng and Haitian. And what we do is we find the optimal value in these, the critical index in probabilistic scaling, which is what we call SPR, which is -1 over p minus 1, which is always lower than the deterministic scaling, as the threshold for NLS with random data, okay? And in particular, we prove that if you give me data in any S which is above this number, not this number, not above, I mean, what is known is above this number, but now I say above this number, which is much lower, then I can always find a solution which exists and is unique in the strong sense for a short amount of time, for almost for data, for random initial data, so almost surely. Okay, and not only that, but what we answer, which for me gives me a lot of pleasure, is that I can give you a very precise description. We can give you a very precise description of how the solution looks. I give you random data and I can tell you exactly how this randomness propagates, at least for a short time. So this is the question of propagation of randomness or propagation of chaos in terms of multilinear Gaussian. So there is a very, very detailed and explicit description. And we also solve, as I said a minute ago, the problem of the invariance and existence of global strong solutions for the Gibbs measure in 2 dimensions for any p. And the reason why we can do that is because the support is just below L2, but you see for any p, -1 over p minus 1 is always a number that is below minus epsilon. So that means that this problem is always subcritical relative to this probabilistic scaling. And this is the reason why we can solve it. So the probabilistic, I want to explain you where this probabilistic scaling comes from. So the heuristics behind the probabilistic scaling it comes from sort of like the square root gain or square root cancellation of the sums of independent random variables, which tells you that, for example, if you sum independent random variables here, instead of this being bounded by n, what happens is sum 1, then this is bounded by the square root of n. So you gain a 1/2 power, or there is a cancellation of the 1/2 power, okay? And so now let me repeat the calculation that I did before for the deterministic scaling. I'm going to do the same calculation, but I'm going to use this fact. And then you will see how this probabilistic scaling comes up. So we start again with the same data, but instead of having a 1 here, I put the random variable, okay? So we randomize the initial data. And we ask the same question. If I take data which has unit size in HS, you give me an S, and this is the alpha that you take. Then as before, then the second iterate, which is this Duhamel of the linear evolutions, should be also bounded. So you do the same calculation, except that now, instead of having just the first part here of the sum, you have all these random variables. And so if you use what I just told you, okay, then instead of summing 1 here, what you end up summing, so you have this. So Here, this K1 being different than K2, K2 being different than K3 is because you want to preserve the independence between the functions with a bar and no bar. So let's assume that they're all independent. So instead of summing 1, if you use this large deviation estimate, then you end up summing, you get 1, but to the power 1/2. You gain a square root. So instead of having n to the minus p alpha, blah, 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 you get this number over 2. And if you do the same calculation, you gain this 1/2 in front of this number, which tells you that your f should be bigger or equal than -1 over p minus 1. So it's thanks to this 1/2 here that the final calculation is different. Okay, and this is where the probabilistic scaling comes from. So let me actually give you some pictures where you can see. Okay, so if I take dimension 2 and a cubic, the cubic equation, then the deterministic scaling is 0, and the probabilistic scaling is -1/2. So it's much lower. So you have a lot of room here. Okay, and in terms of the Gibbs measure, if you are in D2 and p equals to 3, then this SG number is 0. Okay, so that means that the measure is supported just below 0. Okay, and this is what Bourgain did. He was able to bridge this gap. Okay, I'll tell you more later. Okay, and one thing that I want to tell you now is that the nonlinear Schrödinger equation is an equation that has doesn't give you any gain when you invert. When you look at the Duhamel, you gain no smoothness whatsoever. There is no gain of regularity from the equation. So that means that if you start in HS, you're going to end up in HS at best. Okay, so this is what happens with the cubic in 2D. If you are in the 2D quintic, then the critical becomes the deterministic critical becomes a half. The measure is supported in the same place, and the probabilistic will be -1/4. But if you're in dimension 3, okay, and you take the cubic, this is the reason why the measure is so hard, because now the critical is the same as in the 2D, I told you, 1/2. But now what happens is that you get a switch. Here in these two cases, the probabilistic scaling is below the measure, the place where the measure is sitting. But here the measure is sitting below this number, or in other words, what is more important, this number 1 minus 3/2 is -1/2, which is exactly the same as the probabilistic scaling. In other words, these two numbers coincide, which means that this problem becomes critical relative to the probabilistic scaling, while this problem is subcritical. So subcritical is good, critical is very tough. Okay, so that's why this is still open. So our results actually with Yuden actually are, well, first of all, that we prove essentially that if you take NES about the probabilistic index, then we can prove that we have the solutions all the way from here all the way up. So this was what was known before deterministically, so we can find solutions all in this range. Okay, Bourgain actually could do it from a little bit below 0 and up. So we gain actually relative in 2 dimensions. In 2 dimensions, we gain all of this. Actually, I would write for all dimensions, not just for dimensions 2. Okay. And then, as I said before, we prove the invariance of the measure, which is actually quite amazing. Let me explain you the following. So what is it that Bourgain did in dimensions 2 for the cubic? You see, he started with data here in SG minus, and in order for him to be able to prove his result, he had to somehow squeeze from nowhere some regularity so that he could actually become larger than 0, where he could grab the deterministic result. Okay. Now, in our case, actually, we need to actually, if you're quintic, we start from the same place, but instead of gaining just epsilon regularity, we need to actually go all the way to 1/2. So we need to gain at least 1/2 derivatives plus epsilon instead of epsilon from nowhere. Okay, because there is nothing in the equation that gives you this gain of regularity. And finally, we have a result which is for long time, which is an improvement of this, but let me not, I'm actually running late, so let me not talk about that. So let me just quickly tell you what is Bourgain's method. So there is something in here that I'm hiding under the rug that, you need to sort of renormalize a little bit the nonlinearity because the potential energy is actually infinity for when you're in the support of the measure. Let me not talk about that. And as I told you before, the scaling in 2D for the cubic is 0, and the measure is just below 0. And our probabilistic scaling is -1/4, so there is a lot of room here. So the idea of Bourgain was to do a linear nonlinear decomposition. So he says, look, I'm not going to try to solve U by a fixed point argument, but I'm going to look for solutions that can be written as the linear evolution of something random plus a term which I'm going to try to show that is above L2, is smoother than this. This is very rough. This starts below L2, stays below L2, but he's going to try to show that this term V is above L2. Okay. So in other words, he looked for solutions that can be seen as living in an affine ball where the center of that ball is the linear evolution of the random data. And the way to do that is to solve for the difference equation between U and this. So you write the equation for V, and what you are facing is you say, well, you want to solve this problem, be a fixed point argument now, because this is for V, not for U. But now your nonlinearity is not cubic in U or cubic in V, but has the interaction of these rough random terms, which is the smooth deterministic terms. Okay, and the way that you do that is like the techniques that you have to use here are these multilinear large deviation estimates, analytic number theory, and an argument that is very, very special to nonlinear Schrödinger, which is some sort of random matrix argument that is related to harmonic analysis, T-star argument. And let me skip, I was going to explain you how this is done, but I'm going very slow, so let me skip this and tell you a little bit about our theory. So how do we prove our result number one? How are we able to find solutions from all the way this very negative probabilistic scaling onwards? Okay. So the result on the measure actually is came before the result of the local well-posedness, and it needs a theory which is much more gentle, which is the theory of random averaging operators. And it was actually it's a precursor, if you wish, to the theory of random tensors, and it's a much simpler theory, which actually suffices in many cases where you're not too close to the probabilistic scaling. So I won't discuss this theory of random averaging operators, but they come in the theory of random tensors because they're associated to what we call the 1-1 tensors. So let me tell you what is a 1-1 tensor. The 1-1 tensor comes as follows. So you take the Duhamel operator I, and you take the linear evolution of a random data. This N means that I have localized my data to frequency capital N. This is the dyadic number. And then the light blue here means that my solution lives at a lower frequency than N. So N to the delta for some delta. And now this configuration, by definition, is the Duhamel of the cubic term, where in the first entry you have the linear evolution of random, and here you have the low frequencies of the solution. So this is actually the key point, which is you need to understand relative to Bourgain, you need to understand what is the interaction between the high frequencies and the low frequencies, but you need to understand the randomness in the low frequencies. You need to put your hands in the low frequencies. You cannot just place them in a function space. You really need to understand what's going on. And you can actually repeat this. You can actually take you can take this term and you repeat. You take the first entry and you replace it by the cubic of the same thing. So in other words, this is this picture, right? I replace this ball by the same configuration. Okay, so in the first entry now I have iterated, and I keep on doing this always in the first entry. So what you are doing really is then if you sum all these three forms, so if you sum all the linear evolution and all of these three forms, okay, let me call that sum this box, and let me denote it by psi n and delta because it depends on n and delta. So what you have done really to sum this series is the same as actually doing a paralinearization of your equation, where you are solving this problem, which is the same equation Schrodinger, where in the first entry, you have this function. So it's linear in here. And then you have, you think of these terms as being some sort of weight. Okay. So in other words, this function, by definition, you can explicitly solve it, is going to be the linear evolution of your data plus a tree where here, instead of having the linear evolution of your data, you have the size. Okay. And you can explicitly compute this. Okay. You can compute the Fourier transform of this function. And what you notice, lo and behold, is that what you get is a twisted Gaussian. So that means that to first order, after the linear evolution, so after the linear evolution of random data, to first order, what you see is a twisted Gaussian. So this term here, HKK1, is what we call the 1-1 tensor. And it encodes the information about the low frequency, the randomness and the low frequency of these terms. Okay, and it's a matrix that is kind of twisting the Gaussian. And so this is actually what is behind the method of random averaging operators, which I'm going to skip. But essentially what it does is it tells you that relative to Bourgain, just focus on this first part. Bourgain only looked for solutions which were linear evolution of random plus a remainder. We put our hands into the remainder and we peel off a little bit more of information about the randomness inside the remainder. Instead of ignoring it and treating it as deterministic, we peel off some and we put it in this term, which is a linear operator acting, that is a linear operator that is given by the low frequency components acting on the high frequency components of the linear evolution of the random, plus a remainder. So the theory of random tensors, actually, if I want to actually go all the way to the probabilistic, to the edge of the probabilistic scaling, then instead of doing just something to first order, you need to consider higher order or arbitrary higher order expansions. So in other words, you repeat these expansions and you stop when you hit some low frequency. This, where do you stop depends on how smooth, say, your remainder you want your remainder to be. And if you do this and you plug it into the equation, then what happens is that you arrive into an answer that says that then the Fourier coefficients of your solution should look like some linear combinations of multilinear Gaussians plus a remainder with coefficients that are the key. These coefficients carry the information about the low frequencies of your low frequency components of your solution. And they are the key objects or the key quantities to be studied, okay? And so the point is that, what you want is to prove good enough estimates in here so that you can prove that you have good estimates in these tensors and in the remainder so that this converges to the solution, okay? And so this is what we call a Q1 tensor or higher order tensor. And they come from higher order iterations of trees, okay? And so an example of a 2-1 tensor comes when, instead of having a single terminal leaf that is the random evolution of Gaussian, you have two of them. If you have two terminal leaves, which are a linear evolution of Gaussian, then this is a 2-1 tensor. And it's just simply the Duhamel of the cubic term with two of them, okay? And another one, and so if you do that, and let me tell you why this is a 2-1 tensor, because if you compute the Fourier transform of this picture, then it looks like this. And so you see what you have is the two Gaussians. And if you write this sum as the characteristic function of whatever you're summing that comes from taking the Fourier transform, and you put this term, which has the low frequency in it, then, and you call all of this, you see this depends on K1 and K2, which are outside. And so this is the definition of the HKK1, K2. So this is an example of a 2-1 tensor. And you want to view this as something that maps, say, K1, K2 into K, as an operator that sort of maps K1, K2 into K. So let me skip the next example. This is another example of a 2-1 tensor, and just tell you a little bit because, Christina, how am I with time?
You have couple minutes at most.
Okay, so let me actually tell you a little bit about the framework and the idea of the proof. So the random tensors, what it does is, you see, I said that you iterate, and here I didn't show this example, but this is also 2 one-tensors in which you keep on iterating, and you have also 3 one-tensors, 4 one-tensors, and so on. And so the combinatorial complexity that you have if you just do things by hand with these trees is just, you cannot handle it. And so what the random tensor framework does is allows you to get a handle into this combinatorial complexity. And what you do is we develop an algebraic theory which focuses on the structure of these tensors, and it tells you how bigger tensors are built from smaller tensors. And we have these operations which are called merging and trimming that come from taking tensor products, contraction, and so on. And they are the main 2 operations in the algebraic theory. And we also develop an analytic theory, which entails, choosing the correct norms to study these tensors and proving sort of estimates that are preserved under the algebraic theory. So you want to prove some estimates and some bounds for this merge of trim tensors. And once you have done that, then the proof proceeds by induction, relying on these 2 theories, large deviation estimates, analytic number theory, and a combinatorial argument, a subtle selection algorithm that allows you to exploit the flexibility that we have built into this analytic theory. So these are examples of merging and trimming, which I don't have time to go through, but essentially this is an example of what does it mean to trim, to merge. And the trimming is actually something very specific, which comes because you need to preserve independence all the time. So you need to trim every time that you have something where independence is lost, you need to trim it. So let me skip this. And let me just tell you something about the analytic theory, and then I'll stop. I mean, what is very beautiful about this, that it turns out that the right norms to study these tensors are the operator norms. Okay, when they operate, these tensors are viewed as linear mappings from functions that send certain part of the variables into the remaining ones. And what is amazing is that the only thing that you need is these L2 norms. That's all you need. Okay, sometimes you need this L2 operator norm, sometimes you need the Hilbert-Schmidt norm, but you don't need any fancy norms. You have built the theory so robustly that the norms that you use are just L2 basic norms, operator norms. And once you have that, you can prove a lot of estimates. And let me just finish by this slide that says that one of the estimates that you prove actually is an analog, is kind of like a very broad generalization of the idea of Bourgain, which is to use and prove by sort of like iterating this TT star argument, this random matrix theory. And we think that actually this estimate, which is in our paper, is very hard to prove by hand, even in the simplest case. But we think that it's of interest in general in the study of random matrices with general Gaussian. And then to finish, let me give you a picture of how these random tensors localize. So they are almost diagonal. So you really have a resolution of the solution as the linear evolution of random plus a matrices which twist the multilinear Gaussians by almost diagonal matrices plus a very smooth term. Okay, and this is how these tensors sort of localize an almost diagonal term. And with this, many thanks for your attention. I'm sorry that I went a little bit over time.
Thank you, Andrea, for a wonderful talk. We have a couple questions. One of them is, why is supercritical data important?
Supercritical, okay. So supercritical data relative to the, it's not that it's important, but it's kind of like you want to know why is it in the deterministic case, you want to say, well, you know, what happens below scaling? I mean, you have a problem in which if you have regular data above the scaling, then you have solutions. If you are critical, sometimes you do, sometimes you don't. But if you are below that one, you know, you could have actually, even in the defocusing case, you can have instabilities, you can have blow up. And so the question that we are trying to say is this okay, deterministically, that seems to be a threshold, But it's actually, is it really a threshold? If you look at the problem generically, is that a threshold? And the answer is no, it's not a threshold. You can go much lower than that.
Thank you. A second question. It says, it seems surprising that the probabilistic scaling is dimensionally independent. Is there
Exactly.
a heuristic explanation for why is the case?
Not really. I mean, not really. It was a surprise to us as well. But as I show you in the calculation, it is indeed dimension independent. Yes.
Mm-hmm. And a third question is, it is crucial that you consider Laplacian. What if it would be a bi-Laplacian or fractional Laplacian?
That's an excellent question. Okay, and of course the dispersive relationships are different. So it's like, you know, your theory is going to be different. So if you have something like a fractional Laplacian, we expect. I mean, I showed you the theory for the nonlinear Schrodinger equation, but if you have weaker dispersion, like something like a fractional Laplacian, we expect the theory. So the theory is very robust in the sense that the only thing that depends on the equation are the counting estimates, the analytic number theory part. That the analytic number theory part is very much equation dependent. So that's going to change if you change the Laplacian by another operator. But the rest should survive somehow. Okay, and of course, I mean, you know, the answer that you have to do is going to be adapted to the equation. But the rest of the theory, the algebraic part and the analytic part, are robust for sort of dispersive PDE. Mm-hmm.
Thank you, Andrea. Oops, there are more something. Oh, so people are saying thank you. Thank you for a wonderful talk. Thank you all the attendees, and thank you again to the AMS and to the JMM.
Yes, thank you everybody. And if you have any questions, I'm always happy to answer. Feel free to look for my email address and send me an email. And thank you for your attention.